Hello Midnights. Thank you for tuning in. Next up, Tunguska, Deciphering the Whispers of 1908, an in-depth examination with essential background and data. Let us know where you are listening from and don't forget to subscribe. On the morning of June 30, 1908, at approximately 7:17 a.m. local time, an unprecedented atmospheric explosion rocked the remote Tunguska region of central Siberia, near the Podkamennaya Tunguska River. This cataclysmic event, estimated to have released energy equivalent to 10 to 15 megatons of TNT, a staggering figure representing 650 to 1,000 times more power than the atomic bomb dropped on Hiroshima, flattened an estimated 80 million trees across 2,150 square kilometers, 830 square miles, of taiga forest. The blast generated seismic waves detectable across Eurasia, disturbed atmospheric pressure sufficient to be registered by barographs in the United Kingdom, and caused luminous night skies, known as white nights, over Europe for several days due to atmospheric dust. Yet, despite its immense scale, the Tunguska event remains an enduring scientific puzzle, primarily due to the absence of a conventional impact crater and the era's limited investigative capabilities. This unique confluence of factors has, for over a century, cultivated a fertile ground for rumors and alternative theories, far beyond the scientific consensus of an airburst from a meteoroid or comet. These whispers, often highly imaginative, are not mere idle speculation but rather reflect humanity's struggle to rationalize an extraordinary phenomenon, filling knowledge gaps with narratives that range from the plausible to the fantastical. To truly grasp the allure and persistence of these Tunguska rumors, a reader benefits from understanding several key background elements. The extreme isolation and harsh environment of the Tunguska region in 1908 played a pivotal role in shaping early understanding and subsequent myth-making. This area of Siberia was extraordinarily remote and largely uncharted territory, far from any established scientific outposts or significant population centers. It was primarily the domain of the Evenk, formerly Tungus, nomadic reindeer herders, with no major roads, railways, or modern communication networks like telegraph lines extending into the steep taiga. Travel involved arduous, weeks or months-long expeditions by riverboat during summer, or by reindeer sled in winter, traversing dense forests and vast, mosquito-ridden swamps. This extreme inaccessibility significantly delayed initial investigations and limited their scope. In fact, the first dedicated scientific expedition, led by Russian mineralogist Leonid Kulik, did not reach the actual blast epicenter until 1927, a remarkable 19 years after the event. This substantial time lag was critical because many ephemeral pieces of evidence, such as initial scorch marks on surviving trees and the precise state of atmospheric dust, had either vanished or been significantly altered by weathering, biological processes, for example, fungal decay, forest regeneration, and natural deposition, for example, peat bog growth, which can conceal smaller fragments. Moreover, eyewitness memories, though invaluable, were nearly 2 decades old, prone to degradation, potential embellishment, and the unconscious merging of personal experiences with circulating local legends, making objective verification challenging. Further contributing to the enigma was the nascent state of relevant scientific understanding in the early 20th century. In 1908, the field of meteoritics was still in its infancy. While meteorites were known to fall to Earth, the concept of a large cosmic object, like an asteroid or comet fragment, entering Earth's atmosphere at high velocity and disintegrating in a massive airburst without leaving a significant impact crater was not a widely understood or scientifically modeled phenomenon. Most known meteorite events involved smaller objects that either created distinct craters or were found as solid fragments. Advanced fields like nuclear physics, which would later inform theories of natural nuclear explosions, sophisticated atmospheric modeling, crucial for understanding shockwave propagation and the unique butterfly pattern, and space physics were either non-existent or in very early developmental stages. Scientists of the time simply lacked the theoretical frameworks, computational tools, and observational data to accurately predict or explain such a complex atmospheric event. Crucially, there were no global networks of seismographs, infrasound detectors, or satellite systems. Today, similar events, even smaller ones like Chelyabinsk, are instantly detected and analyzed globally by a vast array of instruments. In 1908, information was piecemeal, relied heavily on local observations, and only the most powerful, globally detectable waves, like the barometric pressure waves, registered on the sparse instruments of the time. This lack of immediate, comprehensive scientific data created a large information vacuum that allowed alternative theories to flourish, often based on speculation rather than empirical evidence. The turbulent geopolitical and ideological context of the 20th century also played a significant role. In 1908, Russia was a vast, autocratic empire on the brink of profound social and political upheaval. The distant Siberian phenomenon was quickly overshadowed by more pressing domestic crises, including growing revolutionary sentiments and escalating international tensions that would soon lead to World War I. This period of instability meant scientific investigation, while pursued by dedicated individuals like Kulik, received limited state support or immediate prioritization. Later, during the two world wars and the subsequent Cold War, scientific research globally, and particularly in the Soviet Union, became deeply intertwined with military priorities and often shrouded in intense state secrecy. This environment of suspicion often led to any unexplained phenomena, especially those involving massive energy releases, being attributed to secret weapons tests by opposing blocs, for example, the US or the USSR, fueling mutual distrust and widespread conspiracy theories. For instance, the striking visual similarities between the flattened forests of Tunguska and the aftermath of nuclear detonations in Hiroshima and Nagasaki fueled early, though scientifically debunked, theories of a natural nuclear explosion or even a secret weapon test by some unknown power, reflecting the atomic age's anxieties. Furthermore, under Soviet rule, information dissemination was tightly controlled, and while Soviet scientists, for example, Nikolai Vasilyev, Kirill Florensky, conducted pioneering and extensive research on Tunguska for decades, their findings were not always immediately or widely shared with the international scientific community. This historical precedent of restricted access to data and a lack of transparent communication could inadvertently foster distrust and allow non-scientific narratives to gain traction outside official channels, particularly in the West. The interpretive challenges of eyewitness testimony are another crucial aspect that fueled early rumors. While providing invaluable historical context, these accounts are inherently subjective and prone to inaccuracies, especially when collected decades after the event. People describe what they perceive, which can be profoundly influenced by fear, surprise, and their existing cultural framework. The closest known eyewitnesses were Ivank reindeer herders and Russian settlers located roughly 60 to 65 kilometers, 37 to 40 miles, from the epicenter. They reported intense heat, being knocked off their feet, and dwellings being damaged, vividly demonstrating the widespread shockwave, even at significant distances. These accounts, however, were not standardized scientific observations. For the Ivank indigenous people, the event was a deeply spiritual and terrifying experience that directly impacted their traditional nomadic way of life, destruction of reindeer herds and vast tracts of forest. Their descriptions often incorporated elements of their animistic beliefs, such as devils, Agdi, descending from the sky, fire gods, or a thunder god striking the earth. These spiritual interpretations were later, in popular media, sometimes taken literally or sensationalized as direct descriptions of alien spacecraft. Moreover, stories passed down through generations or relayed through multiple intermediaries can become embellished, exaggerated, or distorted from their original form, a classic telephone game effect. Kulik's expeditions, conducted years later, had to contend with these layered narratives, making the objective reconstruction of events more complex. The psychological impact on the local population, who suffered immediate and prolonged hardship due to the destruction of their resources and traditional hunting grounds, is often overlooked but profoundly shaped their initial understanding and subsequent cultural memory of the event, influencing their economic survival and social structures for years. Finally, the enduring human fascination with the unknown and the sensational continues to fuel the persistence of these rumors. While a natural meteoroid airburst is a scientifically awe-inspiring event, the idea of an alien spaceship crash, a secret superweapon test, or a bizarre natural phenomenon, like antimatter annihilation, often holds a greater appeal for the popular imagination. The human mind frequently seeks the most dramatic or mysterious explanation for unexplained occurrences, particularly when faced with a lack of immediate, definitive answers. This inherent human tendency to fill knowledge gaps with compelling narratives, combined with the extreme scale of the event, created a perfect storm for the proliferation of conspiracy theories. During times of widespread societal mistrust or perceived government secrecy, such theories can gain significant traction. For example, the mid-20th century saw a dramatic rise in UFO sightings and popular interest in extraterrestrial life, partly fueled by post-World War II advancements in aviation and rocketry, and the emerging Cold War paranoia. The Tunguska event, with its lack of a conventional impact object and immense power, naturally became a prime candidate for alien crash theories, easily fitting into the broader UFO phenomenon that gripped the public consciousness. This constant exposure to sensational narratives in books, Documentaries, internet forums, and social media platforms, often without critical scientific vetting or proper distinction between established fact and speculation, ensures that the Tunguska rumors remain widely known and frequently discussed in global popular culture, sometimes overshadowing the robust scientific consensus. The historical trend of blending fantasy and science, particularly prevalent in Russian culture, also meant that science fiction authors like Alexander Kazantsev could popularize the alien spacecraft theory shortly after World War II, further cementing it in the public imagination, demonstrating how cultural narratives can powerfully shape the interpretation of unexplained events. The enduring allure of these alternative explanations for Tunguska is like a Rorschach test for humanity's anxieties and aspirations. What we choose to believe about this unexplained event often says more about our fears of unknown cosmic threats, our distrust of powerful institutions, or our yearning for extraterrestrial contact, than it does about the event itself. The sheer scale of the Tunguska event is best understood through concrete measurements. The explosion generated seismic waves equivalent to an earthquake of approximately magnitude 5.0 on the Richter scale. These tremors were recorded by seismographs as far away as Irkutsk, about 970 kilometers or 600 miles away, and even in Jena, Germany, providing objective, instrumental data of a massive energy release. Atmospheric pressure fluctuations caused by the blast were detected by barographs across Europe, including in the United Kingdom, for example, London, and Germany. These infrasound waves are estimated to have circled the globe twice, demonstrating the global reach of the atmospheric disturbance, far beyond any conventional explosion. For several nights following the event, from June 30 to early July, the night sky over large parts of Europe, including Scandinavia, the UK, and parts of Russia, was unusually bright. People could reportedly read newspapers at midnight without artificial light. This white nights phenomenon was attributed to dust and ice particles from the disintegrated object and the subsequent atmospheric disturbance reflecting sunlight, indicating a large quantity of material injected into the upper atmosphere. Furthermore, the flattened trees at the site exhibit a distinct butterfly or elongated radial pattern, with trees pointing away from a point several kilometers above the ground, not directly from a ground impact. This pattern, meticulously mapped by Kulik's 1927 expedition, is a signature of an object entering the atmosphere at a shallow angle and exploding in an airburst, where the elongated shock wave dictates the direction of the tree fall. The most significant and persistent enigma fueling Tunguska's rumors is the glaring lack of a discernible impact crater. Unlike typical meteorite falls, which often create a bowl-shaped depression, no such feature was ever found at the presumed epicenter. This crucial absence became the genesis for virtually all alternative theories. Early swamp gas theories, for instance, vaguely suggested a massive release and ignition of natural gas from the region's vast peat bogs and swamps, a crude hypothesis that was quickly dismissed but underscored the initial difficulty in conceptualizing the event. Similarly, the terrestrial volcanic/explosion theory posited a colossal underground volcanic eruption or a sudden release of combustible gases from the Earth's crust, pointing to widespread scorching and radial tree patterns. However, extensive geological surveys by later Soviet expeditions found no evidence of a volcanic vent or seismic activity indicative of such an eruption, with the atmospheric nature of the blast definitively disproving this. As the 20th century progressed, marked by rapid advancements in physics and the dawn of the space age, the Tunguska rumors grew increasingly exotic, often mirroring contemporary scientific anxieties and fascinations. The natural nuclear explosion hypothesis, emerging after the atomic bombings of Hiroshima and Nagasaki, suggested a natural nuclear explosion from a high-density element. However, rigorous analysis of soil, tree rings, and peat bog samples consistently failed to detect elevated levels of long-lived radioactive isotopes characteristic of a nuclear detonation, largely disproving this theory. The antimatter annihilation theory proposed a fragment of antimatter colliding with Earth's atmosphere, annihilating with matter in a massive energy release. While theoretically capable of such an explosion without residual mass, the existence of macroscopic antimatter traveling through space is astronomically improbable, and specific gamma-ray burst signatures were not detected. Similarly, the microscopic black hole encounter theory, while exploring exotic physics, remains firmly in the realm of speculation, lacking any observational support for its passage or the detection of its specific gravitational and energetic signatures. Perhaps the most widely circulated and culturally persistent Tunguska rumor is the UFO crash or alien intervention. This narrative posits an alien spacecraft, either malfunctioning or deliberately intervening, exploded over the region. Proponents often cite ambiguous eyewitness accounts of fireballs or cylindrical objects, Though consistent with meteoroid entry, the radial blowdown pattern is evidence of an artificial craft, though consistent with airburst models, and alleged anomalous materials or radiation, though never scientifically substantiated and often attributed to misidentification. The UFO theory often thrives on perceived gaps in the scientific explanation, filling them with extraterrestrial narratives. A darker, more conspiratorial vein of Tunguska rumors suggests a human origin. The Nikola Tesla theory, a highly speculative modern rumor, links the event to the eccentric inventor Nikola Tesla, claiming his wireless energy experiments caused the explosion. However, there is no credible scientific evidence or historical documentation to support this. The energy required vastly exceeds anything Tesla was capable of, and the geographical distance renders a direct connection impossible. Similarly, the secret weapon test rumor, popular during the Cold War, suggested a failed weapon test by an unknown power. Yet, no nation possessed such explosive capability in 1908, nor could they have concealed its origin. While the overwhelming scientific consensus, based on decades of rigorous research, modeling, and analysis of all available evidence, points to the Tunguska event being an atmospheric airburst of a stony meteoroid or cometary fragment, the rumors persist. The current leading hypothesis suggests an approximately 50 to 100 meter, 160 to 330 foot, object composed of stony material or ice, entering Earth's atmosphere at a shallow angle, which then disintegrated and exploded at an altitude of 5 to 10 kilometers, 3 to 6 miles, above the ground. This airburst model perfectly explains the radial tree fall, the lack of a crater, the absence of large meteoritic fragments at the surface, and the atmospheric phenomena observed. This model has been further strengthened by comparisons with more recent, well-documented airburst events. A prime example is the Chelyabinsk meteor event in Russia on February 15, 2013. This similar, though significantly smaller, airburst involved an object estimated to be about 17 to 20 meters, 56 to 66 feet, in diameter that exploded with a yield of approximately 440 to 500 kilotons of TNT. While causing considerable damage, shattering windows, injuring 1,500 people, mostly from flying glass, and being widely captured on dashcam videos, Chelyabinsk was still roughly 20 to 30 times less powerful than Tunguska. Crucially, the Chelyabinsk event provided invaluable modern data on asteroid airbursts, greatly strengthening the scientific models applied to Tunguska and helping to definitively rule out many of the alternative theories that had previously gained traction due to a lack of observable analogues. It demonstrated conclusively that an object of a certain size does not need to reach the ground to cause widespread devastation. The Tunguska event's profound legacy also extends to its impact on historical events and trends. Beyond the immediate scientific curiosity, it serves as a stark reminder of the vulnerability of Earth to cosmic impacts, a realization that gradually influenced global space policies. The event's immense destructive power, coupled with the understanding that such an airburst could devastate a large metropolitan area if it occurred over one, slowly but surely spurred scientific and governmental interest in planetary defense. This trend intensified particularly in the late 20th and early 21st centuries, leading to the establishment of near-Earth object (NEO) detection and tracking programs by organizations like NASA. These programs are dedicated to identifying and monitoring asteroids and comets that pose a potential collision threat to Earth. In fact, the United Nations officially declared June 30, the anniversary of the Tunguska event, as International Asteroid Day in 2016, specifically to raise global awareness about the importance of tracking and studying asteroids and to promote international cooperation in planetary defense efforts. The Tunguska event, therefore, stands not just as a historical anomaly but as a pivotal moment that underscored Earth's cosmic precariousness, influencing long-term scientific priorities and international collaborative efforts to protect our planet from future celestial encounters. This demonstrates how a seemingly isolated historical event in a remote corner of the world could have far-reaching implications, shaping scientific endeavors and global policy trends that continue to this day. What happened in 1908 is far more than just a historical anomaly. It is a rich tapestry woven from threads of science, history, politics, economics, and human psychology. Scientifically, it serves as the quintessential example of a powerful cosmic airburst, a rare but devastating phenomenon that demonstrates Earth's vulnerability to celestial objects and has profoundly shaped the modern discipline of planetary defense. Historically, its obscurity for decades reflects the geopolitical turmoil of early 20th century Russia and the limited technological capabilities of the era, delaying thorough investigation. Politically, its aftermath, particularly during the Cold War, became fertile ground for state-sponsored secrecy and the projection of anxieties onto unexplained phenomena. Economically, the immediate impact on the Event people was a devastating blow to their traditional livelihoods, forcing adaptation and highlighting the fragility of indigenous economies in the face of sudden environmental catastrophes. Psychologically, Tunguska became a blank canvas onto which humanity projected its deepest fears, from unknown cosmic threats to secret weapons, and its grandest aspirations, alien contact, mastery over nature, creating persistent rumors that tell us as much about ourselves as they do about the event itself. Ultimately, Tunguska is a powerful reminder of the universe's unpredictable nature, humanity's evolving scientific understanding, and our enduring fascination with the profound mysteries that lie just beyond the veil of our current knowledge.